I'm going to be talking to you today about my PhD research. So I am over at the University of Western Australia within Ausgrav, but also working with a bunch of other universities that aren't within the Ausgrav Odin collaboration. In particular, one of my supervisors, David Tregust, is an education researcher based out at Curtin University. So for those of you who don't know me, maybe if my clicker's going to work. There you go. Previously, I've done research in gravitational waves here at Monash. That was way back in 2017. And then I moved over to the University of Melbourne for a few years and did some research in quantum liquids, so looking at theoretical models of Bose-Einstein condensates. And then during all of that time, I was working on a lot of different outreach projects. So I was doing things where I was presenting in some classrooms, doing some teacher professional development, worked at a place called Science Gallery for a few years, did some volunteer trainings. I still do some of the trainings at UWA for the Ausgrav headsets. But all of that time, I really wanted to find out how to make the programs more effective. And instead of just going off, doing a once-off program, and then never hearing from the students again, I wanted to know how to do it better. So that's kind of how I ended up with the PhD, where I'm learning all about educational research. And the group that I'm doing it with is called Einstein-First. And we're essentially a team of educators, researchers, science communicators, industry experts, and a whole lot more who are all working to modernise the Australian physical science curriculum. It's the big picture aim. We want to change the way that physics is broadly taught in Australia across the country, which is a pretty ambitious goal. So this is an image of the team. So there's a number of PhD students, postdocs, like I said, education researchers, just a wide range of experiences. They're all working together. And essentially, Einstein-First began about 10 years ago. So at that time, we had David Blair, who's experienced in physics research, present some activities to a group of students in year 6. So that's about 12 years old. And we found there was a short-term effect, but also my first project with the group was finding that there was also a long-term impact. Those students who did a whole bunch of hands-on activities to learn about curved space and light as photons could still remember a lot of the activities and the connected concepts 10 years later. And none of those students that we contacted had done physics at university. One of them had done it in year 11 and 12. So that meant, because of the way the curriculum is structured, they knew that mostly because of that short-term program. And that was really good that they could remember it in the long term, because in those 10 years since, Einstein-First had grown quite a lot. So if they hadn't remembered anything, that wouldn't have been a very good result. So Einstein-First has grown and evolved, and we're now having teachers presenting content in the classroom. And we've also now extended to finding ways to teach quantum spin in the classroom at middle school, so 14 to 15-ish years old. And so that was my latest work, has been beginning that process. What are some of the activities we can use, the limitations, any misconceptions that we could potentially be introducing, because there's quite a few with quantum spin. And then hopefully that will then evolve further and further and further. That's kind of broadly what Einstein-First is. My PhD has had 2 key aims. The first one was to create an appropriate learning sequence that facilitates student understanding of the quantum description of light at year 9. A lot of buzzwords, a lot of terminology and jargon. So my talk today is really going to focus on this first aim. My second one was about conceptual and pedagogical knowledge that teachers need to be confident. And I'm not really going to talk about that one today. It's probably not even really going to be in my thesis. It's one of those big extension aims. It'll be the future work. So today we're going to talk about this first aim. And so I'm going to break down each of these chunks of jargony words, the technical language, describe what it means, what I've done over the last 3 years, and some of the results. So to start, what is an appropriate learning sequence? This requires a bit of a plan, because if you're developing a sequence, you need it to be structured. It has to make sense. To do that, we want to collaborate with teachers and school kids as well. Figure out the best way to put this in schools across Australia where we don't need physics experts in the classroom. So first step, we've got to find those schools. We often do that at teacher conferences. So there's an organisation we work with called the Science Teachers Association of Western Australia. They have annual conferences where we present sessions, recruit schools through there. Then, once we've got a school on board, we have to train the teachers. Teach them all about the physics, the concepts, and the activities. So this is an example of some teachers learning how to use a wok and some magnets to teach about geometry on curved space. So in this activity, they start with a whole bunch of the magnetic posts close together, measure the internal angles of a triangle. Surprise, it's 180 degrees. They make it bigger. Now the internal angles do not equal 180 because you're now in a curved space. So that's an activity that we include in year 7, I believe, just teaching about curved space geometry. Train teachers how to do that. Then, once we're in the classroom, the students are going to do a pre-test. We need to know what they already know so that we can see if there's any changes. And those tests usually have combinations of short response questions, diagrams, and a few multiple choice items. This is an example of a pre-test question that I use in the year 9, and we're going to be coming back to this a bit later. All right, they do the pre-test. The teacher presents the module. The students learn the content, they do the activities, and they learn all of the relevant Einsteinian physics concepts that we've chosen. And then, surprise, they do the post-test. So they get similar questions. Usually they're mostly the same, but there's often some extensions, some additional concepts that we really didn't expect them to know beforehand. For example, this question is asking students about a phasor wheel, which is just an activity that we use in the classroom, but we can't expect students to know what a phasor is at year 9, so we don't ask in the pre-test because it's just going to be 0. And then we also do some interviews because just written responses on tests aren't going to give you the full description. You're not going to be able to tell the full story. Then analyze all of the data. So with the tests and the interviews, we have a mixed methods approach. And this is an example of some of the test scores and the way that we can break apart these items. Again, I'm going to be talking about some of this later. Finally, analyze all the data, re-revise. What concepts worked, what didn't, what do we need to improve, what is the data telling us? And we start the circle again, keep going and going. But in reality, it's not quite that simple as a loop. In education research, there's something called the model of educational reconstruction. And I'm going to go through it in a little bit of detail here because it's kind of interesting, but it's also a lot more messy than that simple circle. So the first part of this model is the clarification and analysis of science content, which is, what are we teaching? What are the concepts, how are we going to improve it, all these recursive iterations. And a lot of my first year of my PhD was this, working on what content we should include. Then it's the research on the teaching and learning. How do students understand? What are teaching methods are we using? The pedagogies, the pre-post-test interviews and observations. Then finally, the evaluation of teaching and learning. How do we structure? So throughout my PhD, I started with the content, I'd develop the tests, I would be presenting in the classroom, then go back and restructure. But it's not quite that linear. In reality, each of these pillars reflect each of the others. So you might do one lesson and realize, that idea was way too difficult, let's go back, do the test, go back in between every single lesson, every week of the term, just constantly revising, which is the teaching process as well. I'm sure many, even people doing undergrad units here have similar processes, but it becomes a lot more messy. So instead, we're just going to focus on this circle. We get a score, train the teachers, do the tests, present the module, post-test, analysis, loop again and again and again. So that's how we develop that appropriate learning sequence. But what actually are we teaching? So that first pillar, one of the early steps, is choosing the physics concepts. And with my Year 9 research, I'm looking at the quantum description of light. And Einstein-First is not the only group in the world who's doing this thing. So there's a whole bunch of people that are working to put modern physics into the classroom. So for example, this Reliquant group are based in Norway, and they teach about quantum and gravity to secondary students. There's other groups, so collaborations between Thailand and Australia, who use high-level conceptual tests at university. And a lot of my data analysis work is based on what these guys have done. And similar quantum stuff at the university level, secondary level, and special relativity at the secondary level, which is also happening in the Victorian curriculum. But what's different is that all of these research groups are focusing on upper secondary. So that's the last year of high school, the second last year of high school. And at that level, there's a certain, you can deal with higher level concepts. You can introduce wave functions to a certain point, a lot more of that quantum descriptions. But at Year 9, the students have no mathematical, it's probably a bit harsh, they don't have any higher level mathematical skills, is the best way to phrase that. So if you tell them this is a wave function, they don't really know what a wave is. So then describing wave function is another step beyond that. So you've got to break it down. And the way we do that is by looking at some misconceptions that these other researchers have found. So one of those studies in 2020 looked at misconceptions about potential wells and tunnelling, which again, it's a bit more higher level than what we sort of want to do. But they found that there were a lot of specific difficulties that students had. In particular, it was a mix-up between classical waves and the wave function. So they described this mix-up with classical waves, 26% of students, and they had this deterministic reasoning in terms of movement. And this was a diagram they used to describe that misconception, where students would think, okay, well, we've been told about wave nature, we've been told about particle nature, therefore a quantum object is both. It's like a particle that moves exactly like a wave, which, you know, some situations you can use that understanding, but it's going to break in most other situations. So this misunderstanding of wave-particle duality as a binary really confuses a lot of students, even up to undergrad and probably even some grad level stuff. So at Year 9, we really wanted to focus on this misconception and breaking it down and talking about wave and particle nature as more of a spectrum with energy connecting the two of them. But because we are doing research in Australia, we have to deal with the Australian curriculum, which is a whole thing that I'm not going to talk about as much. But at Year 9, there are certain learning statements that the teachers have to address within the broader Australian curriculum. States can implement these ideas in different ways, but in WA, they just use the Australian curriculum. So we're going to deal with that. What teachers have to tell their students is that energy transfer through different mediums can be explained using wave and particle models. Surface level, that's not bad, right? Like, we can use all of these descriptions. But the way that the elaborations add more detail to this really highlights that binary. So teachers can discuss the wave and particle models, so separate. How can they help us understand aspects? Exploring the properties of waves, understanding the processes underlying convection and conduction in terms of the particle model. And then also a bit about energy that, for my research, I don't really care about. It's still important, but for the sake of this, I'm not talking about it. But the way the curriculum is described, it's very binary. It's one or the other. And most teachers in Australia don't have graduate level physics knowledge. I think it's 60% of teachers in Australia don't have, I think, even an undergraduate physics description, physics knowledge, which makes this, dealing with the nuance of wave-particle duality, really hard if you don't have that training. So what happens in classrooms is students learn about waves, learn about particles, and they kind of hear that light can be both, but we're not going to deal with that. Worry about it later. So in Einstein-First, we have created a quantum description of light that deals with 4 key concepts: photon properties, interference, probability, and energy transfer. Today, I'm really only going to talk about the first 2, but we also include probability and energy transfer in the curriculum. So these are the concepts that we teach. We have photons are packets of light energy. Photons have both waviness and bulletiness. I'll describe those in a minute. Energy connects waviness and bulletiness. Photons transfer energy. Waviness of photons is connected to probability. Bulletiness of photons is connected to momentum. Each of these concepts have multiple activities that students do over a series of lessons. So these concepts turn into about 8 lessons that can be covered in up to 10 class sessions. But it gives a bit of a structure. And so this idea, waviness and bulletiness, was developed in Einstein-First, well before I got there. So I am rolling with it. But effectively, we're saying bulletiness is connected to momentum. More bulletiness, more energy. Those are like your UV photons, your gamma rays. And then at the other end of the spectrum, if you've got low bulletiness, low momentum, that's your radio waves. And then we then connect that to waviness. So you can have high bulletiness, short wavelength, that's your high energy photons, and then low energy, longer wavelength, your radio photons. And by using this bulletiness, waviness, we're trying to get rid of that binary. There's always a bit of both at the same time. And then we can use things like arrows and counting, so statistical measures, to describe our observations with them. So we can describe things like our interference patterns through arrows, things like that. I'm not going to talk that much about the physics. I'm going to be around today and tomorrow, so if you have questions, you can talk about that, and I will bring in some of the activities tomorrow, because I forgot today. All right, but you might notice something similar in these model photons. They match that diagram of the misconception that we saw in the previous work. And part of that's intentional, because by having a model, you can then describe what's wrong with it. Students can make it, get some of these connections, but then we go, okay, in one situation this works, this situation it doesn't. It talks more about the nuance of science. But also, how do we get around that? How can we actually make a model photon when we ask different physicists, you're going to get different answers about what a photon actually is. So that's just one of the limitations that we have to work within. Okay, so those are the concepts and a bit of the learning structure. So now I'm going to talk about measuring understanding, because I want to facilitate student understanding. To do that, you need to dive a little bit more into the education framework, is what they call it. So within Einstein-First, we work from year 3 up till year 10. And we use this thing called a spiral curriculum method, where we introduce ideas once early on, but we introduce it with that higher level sort of understanding. So we're teaching kids in year 3 about phonons, which most of you probably didn't hear about phonons until 2nd, 3rd year undergrad, maybe. But at year 3, we just say it's a little chunk of vibrational energy. Students know what energy is, they know about vibrations, and we can leave it at that at year 3, and then revisit it as they learn more and more about the physics behind these processes. So we build up. And then my work sits in this penultimate year. But the reason we structure it like this is because broadly, modern physics education has focused on those mathematical models and not the conceptual understanding. So by using the concepts of phonons instead of the harmonic oscillator descriptions of a phonon, we can teach that at year 3. And we have found that students do understand these ideas. The main issue is that they get confused between photon and phonon, because just language, T and an N. So we're working on ways to fix that. And so we focus on that conceptual understanding rather than making assumptions, because some teachers think, well, you can't introduce this idea of a phonon, it's too hard. We're like, If you do it appropriately, it's not. Because kids are always filled with why. They want to know, why is the sky blue? Why this? Why that? So we can describe it to them. And they're content. You tell them everything's made of atoms. They're like, cool. Tell them heat is photons. They'll be like, cool. And so this pedagogy gives that great explanatory power, helps answer the why, provided that we're using the right language at the right times. So measuring understanding is difficult. It's not something like maths where you put it on a scale, calibrate your scale, there's your measurement. Understanding, it's a lot more abstract. And you can really delve into the philosophical discussions of understanding. Those types of papers I find really hard to read, so I don't. Well, I do read them, but I just accept what a lot of those education people are saying and apply it. But this pyramid here is a generally accepted way to look at understanding. And it's called the Bloom taxonomy of conceptual understanding. And it starts with a base level of remembering, then you can understand, apply, analyze, evaluate, create. But you might notice it's got the word understand to describe understanding. Part of that is because I am simplifying the education research. Specifically, this is called the revised taxonomy of the cognitive domain. And it's not just a pyramid, it's a weird 3D structure where you've got cognitive processes on one end, knowledge dimension on the other, and they're both kind of cumulative, so they can add, and then you get all these different weird levels, and then you can use different verbs and adjectives to describe your learning objective, which you can then use to create your measure, which is a lot. So instead, I want us to focus on the simplified pyramid. So we can use this to develop ways to interpret what understanding can mean with different contexts. So can the student in year 3 remember what a photon is compared to a phonon? If they can they then understand that when we put our hand in the sun, photons hit our hand and then are creating phonons because our hand's heating up? Can they then apply that to why our chocolate is melting if we leave it in the sun? Just building up all of these different examples. And each of our lessons are designed to develop this understanding. So throughout that spiral curriculum, we build students up from that remember up to create. So each year level, but also each lesson builds through that. All right, so now we need to put it all together and the data. So the data that I'm dealing with, I've collected over the last 3 years, but it's also based on the work of a previous PhD student. So I've started by looking at work that was done by Rahul back in 2021, and he developed a lot of the activities that I've used in the classroom. And so I've taken what he did and created the series of 8 lessons that take students from an assumed no initial knowledge of photons. Because even though Einstein-First works from year 3 up till year 10, I don't have students yet who have done year 3 up till year 8, so I can't assume that they have that base level of knowledge. So that's just an assumption I have to make. And then once we get those other year levels done, my year 9 is going to change again. But the basic ideas will be the same. And we lead them to this quantum description of photon interference. What I did is I was then presenting these lessons in schools in Perth. And because ideally we want the teachers to present this. So in that loop, I said we had that teacher training section. Because I was still developing the content, I had to be in the classroom. So I could immediately see if an activity wasn't working and change it on the fly, which happened a few times. So I have that background knowledge, whereas most teachers don't. So this was 1 lesson a week in 5 different classes in 2 different Perth schools. It was over a period of 2 years. So I was very busy a few of the times. But one of my trials, so I had 4 separate trials. One was majority teacher presented. So I got to that stage where we could have teachers presenting. Then following that model of educational reconstruction, fix the lessons. All right, to some of the results. So I had a total of about 112 students whose data I'm actually able to use. So a downside of working in classrooms and with students is that I need to get parents' ethics approval from the teachers, from the principal, and from the students themselves, which meant there's a pretty low return on some of those students. So of my 112, 38% were from one trial, 5 from another. This one was a struggle. A lot of these 2022 trials happened when COVID was at its peak in WA. So, they're the usual 2 years behind everybody else. So that meant I had a lot of students missing class as well, and parents didn't want to have to deal with extra paperwork. It was hard to get things back. And so I also had students who would maybe do a pre-test but not the post, or they did a post and not the pre, or they just missed so much content in the middle it wasn't worth using their data because they just missed all of the activities. But I still have enough that I can do some stuff with it. And then this last trial, the teacher presented 6 out of the 8 lessons. They got taken on secondment in the end of the term, so then I had to come in. So again, struggles of working with schools. In general, pretty even gender separation. And I also interviewed a number of students across these trials. So data I'm going to show you now is largely from this first trial. This was my first time presenting in the classroom, and it shows a lot more of the variation in the pre and post tests, and I can use it to tell the story of how I've then improved things later. I'm also going to briefly refer to trial 4 because it was the last one. All right, so now we're going to deal with a lot of bar charts. So this is a plot of the total scores from trial 1. On the x-axis, we have each individual student who participated in the trial and their total percentage score. The blue is their pre-test, the orange is the post-test score. And you can see post-test generally higher than the pre, which is good. The students have learnt something, but there are some exceptions. There's 3 different students whose post-test score went down. For 2 of these, number, 9 and 14, I think, there was one item where students have to match wave images. So label them 1, 2, 3, 4. These 2 students got them all right in the pre, but they swapped 2 in the post. So that meant they then lost 2 marks. So that's what's brought them down. And this last one, I've still got to look through in detail, but I think it's because my pre-test had a different total score than the post. So the percentages aren't exactly even, which is a downside to showing these total scores. But in general, we can see the mean score improved, standard deviation about the same. So the total scores are useful, like the students learned something. The initially lower achieving students had really significant increases. So we can say, they've learned maybe a lot more than the higher achieving ones. But it doesn't really tell the full story. So instead, we can do some more interesting statistical analysis to these items. And the one I'm going to talk about most today is something called a difficulty index, which shows the number of students who got an item correct. So if it's a higher value, it was an easier question. And we want this to increase between pre and post because you want the test to become easier because the students have learned something. So here we go. The x-axis is now each item on the test. And we've got our difficulty up here. So if it's higher to 1, it was easier. And there are 2 items that only appear on the post-test. So the 0 in the pre doesn't mean students got it wrong, they just didn't see it. So what I'm going to do is really focus on a few of the items. There were 5 that were purely relating to photon properties. So we had students describing what a photon was or some of the properties. They had to see this interference diagram and deal with some phases. But in particular, we're going to focus on these 2 items, which are the same ones I showed you right at the start. So for this question, students were asked, a strand of hair is placed in the path of a laser beam. What will happen to the light as it passes the hair? So they had to describe it and then complete the diagram below by drawing the pattern. So I was looking at in words and also a diagram, see if they match. So this is what students see. You get this interference pattern where the line of dots are appearing perpendicular to the hair. This laser isn't powerful enough to demonstrate with my hair, but you can see it. And students do this activity in class. It happens multiple times. So they've seen it, they should be able to describe it. All right, so now we're just focusing on these two items. You can see in the pretest, there was one student who made the prediction right. None of them drew the diagram. And then these two were the only pretest. So what I'm going to do is show you some examples of what the students said. First one, if it is hot laser beams, the laser will be so hot it will pass through. So the student thinks the laser is going to melt our screen. The numbering is different because just each test had some different items and ordering. But one student, yeah, they had an idea, probably from movies. Lasers are hot, they can melt things. So that was one response. Another one, the light would stop, and they draw this diagram, which I describe as like a coffee bean shape in my notes. And this was a common response. Most students have this really classical understanding of what it means to block light, which makes sense, because if in school all you're taught is the wave model or the particle model, in that binary, you'd see ray diagrams all the time. You put your hand in front of light and it's going to block, which is true. But now we're dealing with hair, which is at about the same size as our wavelength. So now we get these weird quantum effects happening, and students don't know about it. This one, the beam will split into two beams of light. So again, a very classical description. But also, this test tells me something else about the students' attitude towards actually having to do a test, right? So they had the highlighter and were blowing through it, and each of their pages are just covered in this. But that's also interesting, right? Like, I know that maybe my test was way too long, she got bored, they, like, a whole bunch of information just from a bit of highlighter. Here I've got one more, and then nothing. It's just going to hit the screen. The head is 0. And this was one of the correct responses. Photons will be blocked by the hair, some won't be, and the edge will be fuzzy, as we don't know exactly where the photons are, the uncertainty principle. I was maybe a bit generous marking this correct, but they were using the photon language. They mentioned uncertainty principle. There's some level of understanding in there. So I've marked it right because it then gives me an idea when I'm analysing the data more about what to look at. But their diagram isn't an interference pattern, so that was wrong. So that gives us some idea, I think that was the last one, yeah, about the pre-tests. So students didn't really know about interference, they couldn't draw the diagrams, they'd never seen the experiment before, which gives me a really good baseline, because now I can see how they went on the post-test. And unfortunately, there were still some of these misconceptions around. So these aren't necessarily the same students that I showed with the pre-test. For this one, the light would shine on the wall with the gap where the hair was. Classical shadow. We also had this part C about phasor wheels. I'm not going to talk about the detail of the answer, but they basically had to indicate bright and dark spots on here, which was something they did in class. And you can tell most of them couldn't do it because it's a quite low post-test result. This is one student who got it right. So they talk about the light will be scattered due to interference. It will create a wing-like pattern across the wall. So they have that idea of like the spots that get dimmer towards the edges, and they've drawn something approximately what you would expect. And they also use the phasor wheels to show bright and dark spots. But again, we still have this shadow image that was popping up. But the response from this student gave me an indication of what might have been happening. So I don't think I was there, so I don't know what you're asking. In the first trial, I only had, oh, sorry, it's another one. This is a really good response. Interference pattern, bright and dark. Unfortunately, it's not perpendicular, which was again highlighted in the lessons. Again, I was generous because they still got it mostly right, but I can talk about what was still wrong later on. Because, like I said, I don't care about the total scores in general. I care about their responses to the items. The scores are just a way of starting to measure that. So jumping back to this student's response about how they weren't there. In the first trial, they only did the hair interference experiment once, right at the end of the term. So, because this student missed the lesson, they had no idea how to respond. So what I've done is I looked how many students skipped this answer. So this is looking at the percentage of blank responses. So students who left absolutely nothing. This last question, students left it blank. They didn't have an answer, they didn't know what to do, which then explains why it was so hard, because they were confused. So by using some of this statistical analysis, I could find, right, question with low difficulty, what went wrong, and it turns out I didn't teach it well enough or often enough. So I went back and revised the test question. Instead of a simple draw some arrows on the diagram, we break it down, describe the experiment, give them examples of what I want, and then they do some extra annotations to it. And we did the experiment more than once. Like I said earlier, they'd do it in, I think, lesson 2, and then again in, I think it was 6, and then 8. So if they miss one lesson, they'll see it again, they'll do it again. And what happened is that we got better responses. So this is still that difficulty index, higher value, easier question. Trial 1 that I showed you before, less than 50% on all items here. By trial 4, almost all of them could draw the interference diagram. The prediction is actually kind of lower. I haven't quite looked into why, but trial 1 had about 42 students. This trial had 20, I think, so it's a bit of a numbers game. But actually, in a meeting with my supervisor before I flew over here, we decided we're going to restructure all the data analysis. So I'm breaking it apart to tell the story a bit better. But broadly, they could understand the interference prediction, and they could answer these questions about the phases, bright and dark spots, a lot better. Still below 50, so there's room to grow, but there's some other factors that will be contributing to that. But also importantly, the number of blank responses dropped. So before, we had about 75% blank responses. Now everything was below a quarter of students. So they're actually attempting an answer. You know, the answer's mostly right. These don't include if the student just wrote IDK, just because I've got to fix my script. But in general, students were attempting things more. They felt a little bit more confident. And so that's how one statistical measure can help fix an item. In reality, there are so many more that we deal with. There's things like the point by serial, KR20, a Cronbach alpha. You look at the significance of values, normalized gains, correlations between items, proportions of all the classes. You can use all of this data to just fill in a really good picture of the student understanding. So I'm not going to talk about all of that. But what did this mean? Was I able to develop an appropriate, I thought I fixed all of them, an appropriate learning sequence that facilitates student understanding of the quantum description of light at Year 9? The learning sequence followed these 6 broad concepts with lots of different activities. And in general, we found that students' understanding of the quantum nature of light changed. They started to appreciate that photons could interfere, and there was this probability that was associated with them. The test statistics have identified ways to improve items. So I gave an example of one set of items, but in reality, I could do that for all of them across all of the tests. They all went through multiple iterations. These adapted tests can be used as a tool to measure student understanding. Because by doing all that statistical analysis, I can then say my tests are measuring what I believe they are actually measuring. We call that they are valid and reliable. And so now I can use those student responses to then see how their understanding has moved in that pyramid. And we also know that teachers can present content, but they still need additional resources. So there are some other contributing factors to the student test results, and that comes up in the interviews. So my next step after I write up all of my statistical analysis is to then deal with the interviews. So I've just got two example quotes here. The first one is that students are aware of the lack of depth in the traditional curriculum. So one student said, "I think Einstein-First is a really good idea because since year 7, every year we do something, and then the teachers are like, oh, we'll get into the advanced stuff in next year." They get to next year and it's the exact same. So a lot of you are probably familiar with that. You do projectile motion for like 5 years in a row. So Einstein-First changes that. The students did see that there was a conflict between Einstein-First and their regular lessons. And that's because when I was in the classroom, that would be one lesson a week. The rest of the time was normal curriculum. So I would get all of the quantum description of light, and then they'd have to deal with the binary. And so they saw that, but it also meant my lessons were taking away from their class time. And so this student says, "I think teacher shouldn't have made it so we had to complete things in a tighter time frame, because then it makes us not as focused on this, Einstein-First, as we're thinking about work we're missing out on." So there was some issues. They didn't quite want to focus on the Einstein-First stuff because it wasn't assessed, but they also found it fun. So that's just one of the issues of doing research in the classrooms as well. So in general, I think I've achieved the first aim by using this research plan in general to then develop tests that help students build their understanding to a higher level conceptual knowledge. And the trial data has given me a lot of information to actually evaluate how students have understood all of that. So check. That'll be, the next 6 months are going to be basically writing up all of my papers, which is going to be one will be on all of these stats, and then I've got to deal with the understanding, and then finally revise all of my lessons to create a module we can publish on the Einstein-First website that teachers all across Australia and the world can implement in their classroom, which I try not to think about too much sometimes, because if I'm influencing student learning across Australia, I want to get it right. So that's my research, but also Einstein-First has a sister project called Quantum Girls, which is starting a after-school STEM clubs, and so I'd be remiss if I didn't mention it. They're organising a hackathon challenge and also interviewing some people as part of a role model video, I guess, that's going to be shown to schools. So if anyone's interested in that, talk to me about it later. But with that, I will leave it there. Thank you.
That was a fantastic talk. My question is, do you guys measure the teacher's understanding and how that correlates to the students at all?
We haven't directly dealt with teacher understanding. We mostly deal with what's called teacher self-efficacy, so how confident they feel about it. And that's usually linked to their knowledge, usually, not always. But I think we've applied for a new linkage grant to deal with a lot of the teacher stuff. Because it's only really in the last year that we've gotten teachers in multiple different schools presenting the content. And we've got some teacher training programs happening as well. So I think we hope to look into it a bit more. But in general, with the teachers, we've mostly just interviewed them afterwards, but primarily focusing on the student experience. Because if the students hate it, there's not much point in doing it. But yeah, I think we want to know more about the teacher impact. Cool.
It was interesting what you said about noticing that students noticed the conflict. Was that just in terms of class time, or were they actually saying like, oh, we talk about, this concept in quantum, that's very different to how so-and-so's explained it to me?
Yeah, it was mostly Einstein-First versus their normal class in terms of time. That student in particular, they were in an extension class, so they were already keen science learners and they cared about their test scores, so they got a bit worried. Some students did, I think back on the interviews, I think they mostly thought about the contradictions in ray diagrams. So they learn a lot about just drawing basic, this is how light goes through. But then when I'm talking about, well, it's a bit more wavy and there's many possible paths that the light can take, that's when they start to get a bit confused, because you can talk about light taking the shortest path, which is true, but also then you've got the like Feynman path integral formalism where it can take any possible path as well. So that's where they do get a little bit confused sometimes. But yeah, it was mostly with the timings. But yeah, most contradictions don't arise as much because we're actively trying to avoid them as much as we can. Yeah.
Oh, but they exist. It's just nuance.
Yeah. Yeah, exactly, which is where the interviews really come in handy as well, because I do ask them some of the same questions that are on the test and match what the student has said to their written response. And sometimes there is a contradiction, like they got the question wrong in the written response, but talking to me, they get it right. But sometimes that's a language thing. Some people don't do well in tests. Maybe their mate sitting next to them just wanted to have a chat. And they just wanted to get it over and done with. So yeah, that's what next step is looking more into that.
Hi. So do you have when you're teaching this, do you sort of use any kind of standing wave analogies to make a connection between, because sometimes if you have like a standing wave or something, it may look as if it's sort of stationary or if there's a maximum there. So you can say it kind of looks like a particle, but it's actually also a wave.
Yep.
Is that sort of figure into these quantum description of light?
Yeah. So using standing waves, sometimes, so when I first introduced the idea of waviness, I get them to use a slinky and then make standing waves with that. And I get them to think about how are you making a wave, and that's you're putting energy into it. And if you do more energy, you get that standing wave. What does that look like? I haven't made that direct connection to, oh, it looks like a particle, because I think we want to try and stop thinking about it, what a particle sort of means, I guess. But we do, because you can use standing waves as well with atomic orbitals, which is the same sort of thing. So making that connection to get your standing wave, which is then your region of probability of finding your particle. So we have done that to an extent, yeah.
So I can understand how you measure these like immediate impacts on the student, but earlier on you mentioned the long-term impacts, but how did you measure that?
Yeah, good question. So with the long-term study, the second author on that paper, Rashan, had found a bunch of the students who participated because we had a connection through the school, and the students did a questionnaire and a telephone interview. And the questionnaire was basically, what concepts do you remember? What activities do you remember? What have you gone on to do, I think? And there was 5 questions, I can't quite remember all of them. And then the phone interview was the same sort of thing. So then what I did is I analysed those responses and broke them up into different themes, kind of. I learnt more about how to do this afterwards, but you could group the responses and count. There were, the concept of curved space was mentioned, I'm just going to say 17 times or something. So that was the most remembered concept, and they also had the same activity. And then I could sort of make pairings between them. And so that's kind of how we found that there was a long-term effect, because they could remember these activities that they only ever did in year 6, which was 10 years ago. And a lot of those activities were connected to an excursion they did up to the Gravity Discovery Centre in Gingin, which is north of Perth, which also researchers found doing excursions really have a big impact as well. So it was mostly the qualitative analysis of responses on that one. It wasn't a test.
Yeah,
other question? So what has to happen from here to get things then into Australian or domestic or like state curriculum?
Yep.
Yeah, good question. So we have talked to the Australian curriculum authorities. They do know that we exist and what we want to do. That is a very slow process. At the moment, there's a new version of the Australian curriculum coming out, version 9, which makes some changes, like introducing atoms and molecules in year 7 rather than year 8, but we want to do it in year 3, so there's a bit of a difference there. But the way we design this is we work within the current curriculum. So with year 9, the way the statement is phrased, we can teach this as it is, but it's upskilling the teachers, it's giving them the knowledge and confidence, it's showing them the materials that they can use in the classroom. So we're kind of trying a grassroots approach now, recruiting students and teachers. So we do have, I think there's one school in Victoria that's already trialling some of our stuff. That teacher did our training program last year. So all of our resources are available on the website for people to use, and they don't have to be part of the research. So a lot of them, they can just take the lessons and give it a go, sort of thing. But yeah, I think next steps, trying to recruit more schools, get more teachers involved, and also keep talking to the curriculum people, getting them to change. So that's part of the reason I'm here. So I'm presenting at the Victorian Physics Teachers Conference on Friday. So starting to recruit some of those teachers and get them to hopefully adapt some of our programs.
Yeah, so this is a really interesting talk. I'm afraid I have a somewhat devil's advocate view or question. So I'm always concerned that even at the university level, a lot of our students know a little bit about everything. They've heard some terms, they've heard some words, they ask them a question and they write down some equations, some of which are vaguely relevant and some of which are completely irrelevant. And then they cannot actually calculate anything and cannot, if it's a theory question, they cannot predict the results of any given experiment, right? And which, and one of my concerns is that we really need to train the students to first deal with the basics and then find once they have the basics down, they understand the basic math, they understand the basic physics concepts, then they can build on that and apply it to more advanced topics. I do understand the benefits of getting students excited by bringing up advanced topics, by bringing up modern science, not just starting them out with 17th century physics, but starting them out with 21st century physics. Sounds very exciting, but are we, in the end, giving them sort of the wrong idea about science? And what I mean by that is, are we telling them that science is really about, playing around with words and concepts rather than actually being able to calculate, is this bridge going to stand up or fall down? Or, what will happen when I, shoot this thing up in the air? Is it going to come down and hit me on the head, or will it fly off to Mars, right? Yep. There's a difference there. And I need to know a precise answer. I don't want to take the risk with falling down and hitting me on the head, right? It's not just an approximate thing, right? So is this in the long run giving people, I'm not so worried about whether, I know most people won't be, or third graders won't become physicists. So I don't really care whether they, really master the physics concepts. What I'm more worried about is, do they get the right idea of what science is actually like by
Yeah, that's a good question. It's definitely something I think about a bit as well. I'd say with this program, kind of like what you said, we're not training everyone to be a physicist or to be an engineer, to have to do the math. And the vast majority of students don't do science beyond year 10 as well. So they don't ever really have to deal with that mathematical formalism, which is kind of why we stop at year 10, so that the year 11, 12 undergrad stuff can focus a bit more on that. But we also think that it's worth including some of these ideas early on, because even though people won't become scientists, they're still going to become part of the world that we exist in. They're going to interact with the modern technologies. They might become politicians, parents, voters, all of that sort of thing. So by including these broad ideas about the physics behind a lot of the technology that they use, we can maybe hopefully make them be a bit informed. Like, so many students at year 9 don't understand that microwaves work because of like a microwave, like the wavelength of light. And then because of that, I had some students think that microwaves were radioactive because of like all those misconceptions that are out there. But as soon as I explained that light is this spectrum with high energy that can cause damage because of the bulletiness, they then see, oh, okay, that's not what's really going on. So we're trying to address more of those broader physics concepts. But yeah, you're right. We do have to think about those more details about how do you do the formula. But I would also argue that the current system doesn't work either. I know I've had to teach a lot of undergrads how to make a general plot. So the current system isn't working, so we could make it better. But yeah, with Einstein-First, we don't deal with a lot of the exact stuff. We do have another student, PhD student, Anastasia, who's dealing with the mathematical approaches, but doing more approximations, order of magnitudes, how big is big, how small is small, to get that sense of scale. Some of the year 7 stuff does a little bit more plotting, terminal velocities and accelerations, things like that. But yeah, it's something we've chosen not to do, but it's definitely something I do try and think about. But also if I try and add more complexity to the lessons, the teachers get scared because they also don't know, which then if they're scared, we can't do it. So maybe in another 10 years, we'll be able to push it a bit further, like what you were saying.